All right, so welcome to the last part of 16100. So you have done all your homework and all your quizzes. All right, so congratulations. And the last part of the course is the team design project. So we have really 4 different deliverables. The first is going to be due next Tuesday, and the second is going to be the Tuesday after that, and part 3 is going to be due on actually Monday of really the last week of the class. And this is not in the evening, but before class time. So this is the last part of the project due. And also the final presentation is going to be on Monday and Wednesday of last week. So I'm going to show you what is the team arrangements in the next slide. Basically, we're going to be having a sign-up sheet. You're going to be basically signing up for the presentation of your project results on Monday and Wednesday. All right. So before we discuss the topic of the project, this is the team assignments. And so we have 32 people in the class, and we are split into 8 teams. And each team is going to submit joint reports and give joint presentations. And just for me to have to spot any potential problems in the collaboration, please also each student individually would be required to submit just a very simple paragraph on Canvas on like how each team member in your team is contributing to the project so far. All right. So if in previous years there are cases where some team members just can't be reached, and these cases I can help with cases if we can spot these scenarios early enough. All right, so the first such project is even before the first deliverable. You should submit one on Wednesday, this Wednesday, right? So if somebody just can't be found, I can try to help you find that person. All right. Okay, any questions regarding this? I'm going to post this on Canvas, or you can just find it through the link on Canvas, right? This is on the same OneNote notebook. Okay, any questions so far? Any problems in this this list and the schedule? Okay. If no, let's introduce what is the topic this year. So the design goal is related to reduction in the climate forcing caused by aviation. You may or may not know that aviation, although it accounts for up to now a small percentage of the total climate forcing of human activities, right? About 3.5%. The problem is that almost all other major human-related activities has bright prospects of reducing the amount of emissions and climate forcings. Like cars are becoming more and more electric, right? Power generation are kind of replacing fossil fuels with other sources. But aviation actually is the toughest one to reduce the climate forcing. So one of the reasons is because a tremendous effort has already been put into aviation, maybe not directly to reduce the climate forcing, but to reduce the fuel cost, right? So essentially, if you look at the 1960s all the way to now, the amount of fuel burn per passenger per mile has been reducing pretty steadily, at least in the beginning. But then it seems like although we are still putting tremendous amount of efforts in like basically making airplanes lighter, more efficient, making the jet engines also more efficient, higher bypass ratio and everything, the amount of return per per time has been plateauing. So essentially, it is now, with the fossil fuel burning jet engines, it is now becoming more and more difficult to further reduce how much emission or how much fuel we spend per passenger mile. And the demand is rising, right? I mean, there is a few blimps due to the pandemic, but now like the airlines are as busy as ever. So there is no prospect of the demand actually declining in the future as well. And for all we know, it may just keep rising, right, for passenger travels. And unlike cars, which can just use batteries to replace fossil fuels, for aviation, we have this tyranny of the rocket equation. Anybody knows why that is the case? Anybody wants to give a have you read about the prospect of replacing aviation fuels with batteries? Yes?
The weight doesn't go down as you travel.
Very good point. The weight doesn't go down as you travel, right? Right now, we burn jet fuel, and jet fuel actually burns away, right, as you travel. So the airplane gets lighter. But that's one of the two confounding difficulties. The other one is what? Anybody knows like what is the other aspect of using batteries? You know, how much energy does 1 kilogram or 1 pound of battery contains compared to jet fuel? A lot less. How much less? About 1/5 or 1/4. That's actually a very optimistic estimate, even, right? I mean, with today's technology, batteries contains, I mean, depends on what you look at, on the order of like 1/10 as much energy as like the same weight of jet fuel. And I actually have a diagram for you that basically outlines the current battery technology in terms of what is the specific energy. That's how much energy is contained per kilogram of battery, versus the specific power. That is, if you have a fixed weight of battery, what is the maximum power you can provide? Okay, if you look at the current newest electric cars, they are roughly over here. So between 100 and 1,000 watts per kilogram, more on the higher end, about like 500-ish, and between 140 and 160 watt hours per kilogram. Right? We expect this to get higher in the future, but only very slowly. So there is nothing revolutionary going on in battery technology that can definitely see a commercial future anytime soon, right? So for the purpose of this project, let's just use this Pareto front as what we can do with battery technology for now. Okay, so the problem about the low specific energy is the following. If you want to complete a flight of a reasonable length, right? So for this project, let's focus on a typical journey from the East Coast to the West Coast with a little bit of a reserve. So let's say 3,000 miles is the target range in this project. All right. And if you want to carry enough battery to make that journey, the amount of battery you have to carry is actually heavier, actually several times heavier than a typical airplane like we are building today, right? So, for example, if you want to carry as much passengers as a 737 and fly from East Coast to West Coast, And if you calculate how much battery is needed to provide that much energy for like a typical 737 sized airplane, the amount of battery is actually way heavier than the 737 itself. Okay, then how about just the building an airplane that's just heavier, that actually contains that much battery? What's the problem?
More battery
Exactly, then you need even more battery because the airplane is heavier. What's the problem with heavier? Like more induced drag, right? The amount of lift you have to provide is proportional to the weight of the battery. So the drag is now proportional to lift squared, right? Induced drag. That means you need even more energy, right, to counteract the additional drag. And the more additional energy requires now even larger battery. All right. Of course, you can increase the span to counter the increased lift, but increasing span would also increase the amount of area, right, and also increase the structure weight. So additional skin friction drag and yet additional battery. So this compounding to make that using battery to complete a long flight. I mean, short flight is fine. If you go from Boston to New York, it's pretty reasonable. You can design an airplane that purely uses battery, but flying from East Coast to West Coast, there is essentially no hope of doing so like in a way that can compete with today's fossil fuel technology. So what are we doing here? There are actually many people thinking about all kinds of very ingenious methods. And the one thing that I learned actually less than a year ago was actually a very interesting idea, is use the ideas of towing airplanes. Right? So what's the idea? The idea is you take off regularly, but then a battery-powered airplane also takes off and starts towing you over a relatively short amount of distance, like 500 miles or something like that. Then that towing airplane finishes off with all the batteries consumed. It lands while a new airplane takes off with a full battery and keeps towing the airplane for another, let's say, 500 miles. And then yet another airplane with fresh battery takes off at, basically you have a relay of towing airplanes like along your route, right, that keeps towing the passenger airplane. So essentially the design project is to scale the kind of a towing which is currently only practiced at a very small scale, like gliders and single engine propeller airplanes, to 737 sized airplanes. So that's really the goal of the project this year. All right. So that leads us to break down the different tasks. As we said in the first week, we are just assuming, okay, so for all the three parts, we are assuming the passenger airplane that's being towed is exactly 737. Okay. But in the first week, we are also assuming we are just modifying an existing 737 to serve as the towing plane. So basically get rid of all the fuel tanks, all the passenger cabins, and replace all of them with batteries. All right. And the towing plane would be towing this 737 for, well, however many miles is something you have to calculate. All right. So if you basically, for the first week, you have to do like an energy analysis to figure out, if you want to complete a journey from East Coast to West Coast, how many of these 737s that's basically filled with batteries you have to use to relay the airplane from East Coast to West Coast. So that's going to be the first week's task. All right. And you have to also do this at several different speeds. So assuming, okay, you are towing the airplane not at the design speed of 737, but perhaps at a little bit slower speed, a little bit faster speed. You also want to do this, try this. Okay, maybe not at the design like at the current flying altitude. Maybe you want to do it higher or want to do it lower, right? What are these? What are the different speeds and altitude affect how many towing airplanes do you need? All right, so that's gonna be week 1. Week 2 is going to be now, presumably, the optimal towing airplane is not going to be exactly the same as the existing 737, right? The 737 is really designed to carry passengers burning fossil fuels. But we are not, for this project, we only have 3 weeks, so we don't want to design the passenger airplane, but we want to design the towing airplane. So can we redesign the towing airplane, right? Should we make it bigger or smaller, right? Should we make the wing higher aspect ratio, lower aspect ratio, right? The fuselage smaller or bigger? So how do we size the towing airplane to make it do its job even better? So that's going to be the 2nd week. Okay, and the 3rd week is now you know how big of a wing, how big of a fuselage, how much it weighs. Can you redesign the wing to make it even better? So that's going to be the 3rd week. All right, any questions regarding to that? Okay, if no, let's actually dive into our 1st week. So the 1st week is really figuring out how many tow planes have to take off and tow it and then land.
Sorry, your mic isn't working. Did you need a mic?
Sure. Yeah, I'll do it. Thanks. It's probably over here.
Yeah,
thank you.
This is for you.
Yeah. All right. Yeah, so how many do we need? And for that, you need 2 things. You need the energy density and the power density of current batteries. So here we just use this line, right, as what we can do today. So we don't have to focus too much on that. I mean, realistically, there is a lot of nuances on using batteries to power stuff, right? I mean, the specific power actually drops as the batteries are getting consumed, and the specific energy, how much energy can be used, actually depends on how fast you draw the power. But let's just forget all these nuances for now and focus on the aerodynamics. The aerodynamics is really how much energy do you need to complete the journey, right? So basically, what you need to do this week is to analyze the aerodynamics of 2 airplanes flying one ahead of another, and to figure out if both airplanes are exactly what a 737 is like today. Okay, how much energy do you need? And divide that by how much energy has to be contained, can be reasonably stored in the 737. If you get rid of the fuel tanks and the passengers, then you know how many of these airplanes can have to take off and land. All right, any questions for that? Yes?
Do you not care about wake turbulence?
Sorry?
Do you not care about wake turbulence?
Do you have to care about wake turbulence? So the answer is you don't have to consider wake turbulence per se, but you do want to consider the effect of the wake to the other airplane. Right, so they are not really flying, they are flying pretty close to each other, and one of the things I would strongly suggest to consider is how much lateral distance would these 2 towing airplanes fly so that it is actually getting the optimal amount of efficiency gain by using the wake of one airplane, right, to reduce the induced drag of the airplane being towed. Does that make sense? So you don't really want the airplane behind to fly in the downwash of the towing airplane, right? Presumably the towing airplane is loaded full of batteries, has a lot of weight. So as it flies by, it has to push the air down just as it passes by. And if you're flying in the wake that's being pushed down, it's going to be, you are actually artificially tilting your lift vector even more backwards, right? Because you are seeing a free stream that is already going down instead of going horizontal. So you're tilting your lift backwards, and that actually introduces additional induced drag. On the other hand, you probably want to just fly just a little bit outside of its wake, so that you are actually getting a lift rather than a downwash. Right, so that's an excellent question. Other questions? If no, so here is some very simple numbers on the wetted areas and thickness to chord ratios, which I presumably you don't really have to use this week yet. And this is the planform geometry of the 737. All right. So, and for the maximum takeoff weight, etc., maximum which for the empty weight and the maximum takeoff weight, which you can subtract and see how much better you can squeeze into an empty 737, you can go to Wikipedia. I mean, these numbers are pretty reliable over there. Okay, so that's all I have to say for this week. The rest of this lecture, as well as future lectures, would be mostly the teams working, and I would be helping you with any questions or any roadblocks you have. And for now, I would encourage each team to just gather together and start thinking about how to get started. Use 800.
The 800.
Let's use the 800. If you see multiple versions of 737, use the 800 as the reference. So let me just make sure. Yeah, because this geometry is actually from the 800. Yeah, regarding if you don't know some of your team members, we'll send out to everybody like their contact information, basically emails, so that you can get in touch with them as soon as possible.
I also missed a good chunk of the.
For the batteries,
so there was a very good question, because the airplane getting towed actually is not really using any fuel, right? So it only needs enough fuel for emergency purposes. So you can see when you're calculating the weight of the airplane being towed, you only need to consider the weight of the passenger, but not the weight of the fuel, because the weight of the fuel is probably negligible. Okay, so another very good question. Should you take the max landing weight or max takeoff weight? What do you think? Landing weight, yes. Yeah, when you redesign it, it's probably a good idea to make it such that the landing gears and the thrust reversal, etc., are good enough so that you can actually also land at the max landing weight. But like if you just modify an existing 737, then yeah, probably you can't load the battery for more than the max landing weight. Yeah, if you can. Yeah, two good questions I got. One is for calculating how much induced drag the combination has. So maybe I'll put a little bit drawing here. On the induced drag, of a two airplane combination, right? So one airplane flies ahead, and so let's say this is the airplane that's ahead of it. like the simplest assumption is that it has two trailing vortices. And assume we have a second airplane, say red, being towed. And the idea is that it probably offsets a little bit, right? So that to minimize the induced drag penalty. And that has its own trailing vortices. Assume the second airplane is behind the first airplane with multiple. So basically the separation is much larger than the span. Then the towing airplane doesn't actually feel the trailing edge vortices of the towed airplane, right? Because the trailing edge vortices are so far behind that the induced flow on this is going to be negligible. On the other hand, the towed airplane not only feels the trailing vortices of the towing airplane, but also the effect of every green vortex on the wing is actually like an infinite vortex as opposed to a semi-infinite vortex, right? Because it extends both very far upstream and infinitely downstream. Right, so if you want to calculate how much induced flow is there on the red airplane, I mean, I would probably split up into several sections. There is one section over here, one section over here, and maybe split the left wing also into two sections and compute the induced flow on the center of each. Right, so that is a way to roughly estimate how much induced drag you're going to have by computing the downwash. If you want to do it more accurately, you may want to split the wing into even more segments and do the accumulation. Does that make sense? Right, that's a way to figure out how much induced drag the whole system has. All right, good. Okay, the second question I got also very good is about the batteries, right? Where we have a Pareto front, and where do we look at on the front, right? What is the combination of specific energy and specific power? So my suggestion, at least for the first week, is actually very easy, because if we can compute the total drag, then if we multiply the drag with the speed, we know how much power is required to counteract the drag. Right? And if you divide that power by how much weight of battery you can squeeze into a 737, you have the specific power. That gives you like the horizontal line. That gives you where vertically you are on this plot, right? So this is basically how much power you have to provide divided by how much the batteries weigh, right? So from that horizontal line, you can compute, okay, what is the maximum possible specific energy the battery can have? And then you multiply that again by how much the batteries weigh, you get how much energy the full 737 full of battery can provide. All right. Yeah, also, don't spend too much time getting like exact numbers. Like there is the project is very open-ended in the sense that there is no exact correct answer, right? So that's why, like at the end, every team gives a presentation. If there is one correct answer, it doesn't make sense for teams to give presentations, right? So you don't have to really spend too much time knowing, for example, calculating exactly what the empty weight is or exactly how much an airplane weighs. I mean, so as long as what you've done makes sense, it's fine, right? I mean, there is no need for exact numbers. Yeah.